Hello, and welcome to the multi-die PG bump optimization demo using the Synopsys 3DIC compiler. What you'll see in the demo is how to create prototype PG structures for a simple example multi-die design, perform some PG-related design rule checking, perform EMIR analysis of the multi-die design, and finally optimize the PG bump configuration using AI and ML. Let's start by creating a bump pattern specification. Here, we specify the desired bump radius, the pitch in the X and Y direction, and the desired shape we want to use for the bump. We will choose a structured bump type, which gives us a regular bump pattern. Next, let's create a region of bumps on the base die using the pattern we just defined. Just draw a region on the die using the mouse, and the region is instantly filled with bumps following our defined pattern. Using the property editor, you can make on-the-fly changes to bump region parameters. Here, we set a boundary margin for our bumps. Now, let's select the bumps we want to identify as power and ground. Select the bumps and use the property editor to assign the nets to the bumps for VDD and ground. The VDD bumps are colored in red and the VSS bumps are in blue. Next, let's create a template we can use to define our proposed PG mesh. Define the layers and the metal widths, vertical or horizontal stripes. We will align our stripes to follow the front side PG bumps. Now we can create the PG stripes by specifying the template and selecting the region containing the bumps. We select the region using the mouse. By saving the command history in a file, we can replay it later when AI will run multiple trials for optimization. Let's check for any DRC issues on our package design. We open the simple package design example and turn on the RDL layers. Here we can see a PG plane and some C4 and micro bumps. Now let's open the error browser and check for some potential DRC violations in our package. Here we see a cut-to-cut enclosure violation on the via layer beneath two bumps. Now you can fix the violation even before the design is implemented. Next, let's turn on a 3D view to take a look at our entire design and zoom into the small example of two face-to-face dies on the large package substrate in orange. Here, we're turning on a power density profile of the design. We select the top die and view its power density value, and it's color-coded in the histogram window. We do the same with the base die. Now, let's look at the EMIR profile and select voltage drop. Select VDD and we can see the IR drop heat map. We can check both VDD and VSS maps. Next, let's open the AI view window. On the left side is a comprehensive chart of all of our AI-generated runs, and on the right is a table of runs with all the metrics and the parameters. The rightmost side shows all the different metrics we want AI to use to determine the quality of our result, such as max voltage drop, die area, etc. Below that are the parameters we want AI to use. In this case, just one, the number of bumps relating to each bump column. Let's go into the summary chart and select a scatter plot, in this case a graph that shows the trend between our QOR parameter versus the number of PG bumps used in each run. The right screenshots show the chosen bump configurations. Now let's look at the trend, comparing the number of PG bumps and the IR drop result. As the number of PG bumps increases, the max voltage drop decreases. Next, let's look at the correlation between the number of PG bumps and the AD score. AD stands for Aggregate Design Score and is an overall combined metric of all the selected metrics. The lower the ADs on the y-axis, the better the result. You may think to just increase the number of PG bumps, but that introduces routing congestion and other issues. We're looking to AI and ML to find that sweet spot trade-off. Finally, let's look at the result of AI and ML optimization of PG bumps. In this graph, you see the green data points, which are the better results, a lower AD score, and the orange points, which are the worst cases. We can zoom in to any area and select any data point, and it will highlight in the run table with all the associated metrics. This is determined by AI as our best implementation. This concludes our demo, and thank you for watching.